Hi, today we are going to discuss a very important topic from classical mechanics. It's about phase space trajectories. Right? Now, in all the previous examinations, year after year, there is one question that often repeats. Okay, one type of question that repeats. Right? That question is to plot the phase space diagram. Right? Or look at a system. The potential will be given, and looking at the potential, you have to choose which among the options will give you the or correspond to the correct phase space trajectory of the system. Alright, so we'll look into this in a little bit detail so that we'll be able to solve such problems without much difficulty. Okay, so we'll discuss the phase space diagrams, we'll discuss phase space trajectories for one-dimensional system. We'll be dealing only with one-dimensional system because that's the only system for which we can actually draw a phase space trajectory. And then we'll discuss in some detail the steps to draw the phase space portrait. And we'll go to examples, problems and exercises. So we'll just refresh a little bit. Okay, so you know that we have been talking about the Hamiltonian formalism, and we said that the whole system is represented by one point in the phase space. Okay, and phase space is the system space for the classical mechanical system, the state space, sorry. The phase space is the state space, right, which means that points in your phase space correspond to different states of the system, different classical mechanical states of the system. We have discussed this thing, alright. So the evolution of the system can be represented by the trajectory of the representative point in a 2n dimensional phase space. Okay, so if you have got a one-dimensional system, you will have a two-dimensional phase space, right? And we know that in order to specify the state of a system completely in classical mechanics, you need to give the position and momentum. Okay, now each point in a phase space corresponds to a definite value for the position and the momentum. All right, so that's why we have a 2n dimensional phase space. So this point we can call it as the representative point. Remember, this is not the trajectory in the real space that we observe. Okay, that's not the trajectory of the real space. It's not the trajectory in the configuration space, but this is a trajectory that represents how the system evolves, how the state evolves with time. Right? This is the past state and this will be the future state, like that. Right? So these are different states. The phase space trajectory or the phase space the phase space trajectory actually connects different states of the system at different times. Okay. Now, this is governed, this trajectory is determined by the Hamilton's equations. Right. Now, if you look at the Hamilton's equations, you see that it gives you qi dot and pi dot. Right. And we said that each point in phase space is represented by qi and pi. In order to specify a point in phase space, you need to give qi and pi. Alright. Now, the Hamilton's equation tells how qi will evolve with time and how pi will evolve with time. Essentially, you are getting some sort of a velocity in phase space. Alright. By qi dot and pi dot, you are getting a velocity in phase space. Alright. So, what Hamilton's equations actually does, what Hamilton's equation actually does is that it gives you tiny arrows corresponding to every point in phase space. Alright, if the system is here in phase space, what is its trajectory, or which way is it directed at one particular instant? That's what actually the Hamiltonian gives us. Alright, so we are getting a little bit abstract here, but it's similar. Right? Now, for example, if you have a three-dimensional space, the position will be represented by x, y, and z. Right, and we can define a velocity field if you know x dot, y dot and z dot, because this will give you an arrow. Actually, it will give you an arrow. It will tell us where the system is actually going. For example, in a two-dimensional space, suppose you have a curve like this. All right, if you know the velocities are given by tiny arrows like this, tangent to the trajectory at the given point. Right. In the same way, the Hamilton's equations actually gives us tiny arrows corresponding to every point in phase space. All right. So we have to get used to this way of representing a physical system. All right. So what Hamilton's equation gives is that it gives a velocity. Right. This velocity has two components. We are talking about actually two n components, all right. We are talking about velocity in phase space. Remember, it's not the usual velocity, it's a velocity in phase space. And what are the components of this velocity? The components are q dot and p dot, okay. Just like the components of velocity in real space are x dot, y dot and z dot. In the same way, the components of velocity in phase space is qi dot and pi dot, and this is given by the Hamiltonian. Okay. So, essentially we have a vector field on the phase space defined by the Hamiltonian H. So, Hamiltonian H, if you have the Hamiltonian of the system, we have already seen that the Hamiltonian governs the time evolution of the system. So, if you have a Hamiltonian of the system, then essentially a vector field is defined in the phase space, all right. What do you mean by vector field? Vector field means that corresponding to every point you have a vector. Right, corresponding to every point a vector is assigned, right. So, we not only have points in phase space, corresponding to every point there is also a vector given the Hamiltonian, right. That's the basic idea. Now, but for conservative systems, all right, for conservative system, what do we mean by conservative system? The total energy is given, all right, the total energy is conserved. What do we mean by conservative system? The total energy is conserved, all right, and the total energy is given by the Hamiltonian. Okay. So, for systems, for conservative systems whose total energy is given by the Hamiltonian, we have seen cases where this need not be the case, but we are talking about conservative system whose total energy is given by the Hamiltonian, all right. Now, the representative point is constrained to a surface. Why is it constrained to a surface? Because since Hamiltonian is the total energy, for a conservative system H has to be equal to E. Okay. The energy is conserved, it cannot change, right. Now, this H is a function of phase space variables q and p, we have seen this, okay. So, h of q comma p is equal to E. This actually defines a surface in your phase space, a surface, this defines a surface in phase space. Okay, I think it's kind of obvious, right. If we have a function of this form, f of x comma y comma z is equal to constant or something, then we have a surface on that space, all right. Similarly, this defines a surface in this space, all right. We can diagrammatically represent it like this. So, we have got the phase space, okay, and the Hamiltonian defines a vector field, all right, and these are surfaces of constant energy, all right, these are surfaces of constant energy. So, if you are talking about a conservative system, a point that starts inside one of this surface will remain in this surface, all right. That is just the statement of conservation of energy. Conservation of energy, that is just a statement for the conservation of energy, all right. Okay. So, yeah, this is usually surfaces are defined in this way, f of x comma y comma z is equal to some constant, right. This is a general equation describing surfaces, okay. You can check these things, right. For example, if you look at this, okay, if you just take this xy plane, okay, just let's look at a simple relation like this, x equal to y, x is equal to y, or x is equal to constant, right, x is equal to constant. We know that x is equal to constant for all values of y, right. So, for example, or y is equal to constant, all right, y is equal to constant is a relation of this form and it will be a line, okay, this in 2 dimensions, this is y is equal to a constant. This in 2 dimensions. So, in 2 dimensions such an equation will give you a line, whereas in 3 dimensions it will be a surface, okay. These kinds of equations will give you a surface, okay. It's some kind of a constraint that relates the coordinates and we have a surface in the particular space that we are talking about, okay. All right. So, this is just the representation. These are surfaces of constant E or constant H. These are surfaces defined by the condition that energy is conserved, all right. These are surfaces corresponding to which, so this means that corresponding to every point in this surface, the energy is the same. Corresponding to every point in this surface, the energy is the same, all right. So, you see that we have got a vector field corresponding to every point in space, and once there is a phase space, once the system is represented by a point on one surface, it will always remain on this surface. It cannot go to another surface, all right. This is all for a conservative system. All right, I hope this is clear. Now, we will be all right. So, for a conservative system, if representative point starts on a surface defined by constant value of h, then it remains on that surface. Alright, that's just the statement for conservation of energy. Okay, I hope that's clear. For a one-dimensional system, the phase space is two-dimensional and we call it a phase plane. Alright, and when we do problems, we are dealing with phase planes. Alright, we are dealing with one-dimensional system for which the phase space is two-dimensional. Alright, two-dimensional. So this is called a phase plane. So the problems that we are doing will be equations. The problems that we'll be doing will be trajectories on the phase plane. Alright, we'll be dealing with one-dimensional system. Now, on the phase plane, we can define an equation like this: h is equal to constant. This means that some function of q and p is equal to a constant. Now, this is a line, alright, this is a line. Just as I said, if you have a two-dimensional space, y is equal to constant or x equal to y or x plus y is equal to constant, these are all lines in this space. Okay, so this condition defines a line. Alright, so if it's a three-dimensional, if it's like a six-dimensional or four-dimensional phase space, then you have got a surface. Alright, but on the phase plane, this equation, the energy conservation equation for conservative system, this equation defines a line. Okay, this means that if for a conservative system, suppose this is the line defined by h equal to e in the phase space, phase plane x and px. Okay. Now, if the system starts at one point, it has to remain along this line because energy is conserved. All right. This is a contour. This is a line that connects all the points in phase space corresponding to the same value of energy, corresponding to a particular value of the energy. All right. So this means that the trajectory also has to be equal to this line, and the trajectory has to match with this line. All right. Because for a conservative system, the representative point must remain on surface of constant energy. Here, the surface of constant energy in phase plane is just a line, all right, and the trajectory is also a line, and these lines have to be the same. Okay, so it's what we have said here. Since the representative points must remain on this line, okay, this line also corresponds to a trajectory of the representative point. Okay, so for one-dimensional systems, we have this interesting fact that the condition for conservation of energy, for conservative system, the condition for conservation of energy, okay, this defines the trajectory also, defines the trajectory of the system also. We are talking about the trajectory in phase space, okay, this defines the trajectory of the system also. Okay, so it's easy. So if it's for example a four-dimensional phase space, okay, in that case the condition for energy conservation will be a surface, all right, and the trajectory will be a line on this surface. I hope this is clear. All right, so for higher dimensions, for higher dimensional system, for example, if you go to two dimensions, all right, two dimensions, the phase space will be four-dimensional. The phase space would be four-dimensional. It's 2n dimension, isn't it? Okay, so the conservation of energy will define a surface, but the trajectory will be a line on this surface. Okay, but for one-dimensional system, this defines a line and the trajectory is the same line. Okay, so since the representative point must remain on this line also corresponds to a trajectory of the representative point. Okay, so this is an interesting thing we will be using in problems. Okay, so if it's a one-dimensional system, we can get the trajectory just by finding the line corresponding to h equal to e for a conservative system. Okay, for conservative one-dimensional system, the complete trajectory on phase space is completely determined by energy conservation equation. Okay, this is not true for higher dimensions, right? Because for higher dimensions, we'll need more conditions to pinpoint the trajectory. Okay, for one dimensions, it's completely given by h equal to e. Right? Now we can gain a lot of information of the behavior of the system by looking at the phase space trajectories. All right, so that's why phase space trajectories are important. Okay, this is why phase space trajectories are quite important. So I have made some detailed notes here because this is an important section and it can be practiced. All right, this thing is normally not taught in much detail in the classrooms. All right, some of you might have learned these things, but normally this is not addressed in some detail. So I have given some detailed notes here. I hope that will be helpful. Okay. Now the important thing is that we need not solve the equations of motion to obtain these trajectories. All right, we can, so there are systems which cannot be solved, but still we can draw the qualitative behavior by obtaining the phase space trajectories. All right, how the system point of how the representative point will trace out a trajectory in phase space. This can be drawn without solving the equations of motion. All right, and even for non-linear systems which cannot be easily solved, with some problems can simply not be solved. All right, but we can gain a lot of information about its behavior just by plotting the phase space trajectories. All right, that's why this is important. All right, the phase curves or phase space trajectories can be sketched as a plot of P as a function of x. Right, because we have got the phase spaces, we have got P and x. So basically what you need is to obtain the phase space trajectories P as a function of x or x as a function of P. Okay, that's what we need. All right. And often it's also sketched in the velocity x plane. All right, v x plane. Right, so either it's in the p x plane or it's in the v x plane. So both cases the qualitative behavior is same, because we know that for the cases that we'll discuss, p and v are related by a constant m. Right, so the qualitative behavior, whether you take p or v, the qualitative behavior in most cases will remain the same. Okay. Now we said that the trajectory is defined by the conservation of energy. So the conservation of energy is given by kinetic energy plus potential energy equal to some energy E. All right. So the phase curve immediately is obtained from this. P of x comma E is equal to square root of 2m E minus u. Right. You just solve this for P. Just solve this for P. All right. And you get P as a function of x and the constant energy. All right. This equation actually gives you the phase plot or the phase trajectory. Okay, so we may not even need to do this thing, but this is instructive, right? Because this says that when E minus U increases, P increases. When E minus U decreases, P decreases. So for a constant energy, if U increases, if the potential energy increases, then the momentum has to decrease. All right. So when the potential energy decreases, the momentum has to increase. Okay. So this is instructive to keep this in mind. It's not very difficult, right? P is equal to square root of 2m E minus U, or sometimes E minus V. All right. Now, in order to plot the phase curve, we go through some of this. I'll just give you an example, all right, just before we go on. For example, if you take a simple harmonic oscillator, we'll be discussing this in some more detail, but I'll just give it to you here. Okay, the potential is given like that. All right, the potential half kx square is something like that. It's a parabola. Okay. So what we have is, actually we'll see that we'll have concentric ellipses for as trajectories. Okay, we'll have concentric ellipses as trajectories. So this is x and p. Now it's easy to understand this behavior because you know about this harmonic oscillator, right? So we start with the high momentum, and if you go away from the equilibrium point, the momentum decreases and it comes to a stop, right? So it's like two things connected by a spring. All right, suppose this is the equilibrium point. If you pull it, if the x increases, all right, suppose this is oscillating. Yeah? So as x increases, p will decrease, right? Because along this line is p will decrease and it will come to 0. Okay, and then p will start increasing in the opposite direction. Am I right? Because it starts oscillating. Then p will start increasing in the opposite direction, and then these are curves of constant energies. These are ellipses. We'll see that these are actually ellipses, right? These are curves of constant energy. So the representative point will remain. If it starts at one point along this ellipse, it will remain on this ellipse. Okay, but that's just an example. We'll go to more details of this. Before that, let's write down some general steps that we can keep in mind to plot the phase curve. Okay. So I hope so far it has been clear. Let's go to the steps. All right. So first thing is that some potential will be given. All right. Some potential energy V as a function of x or U as a function of x will be given. The first thing is to plot the potential. All right. The first step is to plot the potential. For example, if you are given the potential is half kx square, we plot this. Right. So it's easy to plot this. We know that this is a parabola. If we don't know, there are other steps that we can take to plot this thing. All right, there are other. We'll discuss this in detail. So let's just take this example of u is equal to half k x square. So first step is to plot this potential. Okay. So that is v of x versus x. This is the equilibrium point. Right? We know that this is a parabola. If you don't know what shape the given potential is, then you have to take steps to plot the potential also. Right? So let's imagine that we have plotted the potential. Okay. Now draw energy lines corresponding to different energies E of the system on the plot for potential. All right. So maybe I can enlarge it a little bit. Okay. So this is how we do it. We first. Okay, sorry. All right, so I'm sorry. So we need to sketch the potential first. All right, so first you plot the potential like that. Okay, so here along this axis or along the vertical axis we are plotting V or U, okay, whichever is the case, and then this is the x-axis. All right, so what does this plot tell us? This plot gives us the potential energy at different points. It gives us the potential energy at different points. All right, so now the next point is to draw energy lines corresponding to different energies E of the system on the plot for the potential. All right, you will understand what we mean by this energy line. So suppose these are possible energies. Okay, these lines correspond to different possible energies. Okay, because the height, okay, the height of this, the height from this x-axis has the dimensions of energy because we are plotting potential, right? So this line means it's a line corresponding to constant energy. This is another line corresponding to constant energy, and we can draw any number of lines. Okay. Let's call this as E1, E2, E3. So we have plotted potentials and we have drawn lines corresponding to different values of energy. Okay. Now below this, plot the sketch P of x comma E is plus or minus 2m E minus U. We saw this already. Okay. All right. So again, we'll take this, below this, it's easier to plot it like this. We plot x along this line and let's say Px, because we are dealing with one dimensional system. Okay, just below this we'll have x and Px, just below this. Okay, now you see that at points where the energy lines intersect the potential energy curve, right? So at this point, this means that at this particular point, at this particular value of x, E is equal to U. That's what it means. Am I right? At this particular point, E is equal to U because these lines intersect. This is the line, this is a straight line corresponding to definite value of energy. This is the potential energy. So at this point, E is equal to U, right? So at points where the energy lines intersect the potential energy curve, the momentum is 0, right? By this equation, the momentum is 0. If the potential increases in a direction, the momentum decreases in that direction and vice versa, right? So let's just drop these lines here. These are points where the momentum becomes equal to 0. So we need to extend this from 0 to both sides. Okay, this is true here also. Okay, all right. Now we have got to start somewhere. Let's start here, or let's start here, right? At some particular value of we have got to, let's see. Right? Indicate the directions of motion of the representative point by marking tiny arrows on the curves obtained by the previous step. Right? So we have to start somewhere. Let's start at some. We could start anywhere on the phase space. Okay, we could start anywhere at the phase space. Let's start at x equal to 0. This point is x equal to 0 and momentum is equal to some value p1. We start here. What happens as you go towards positive x? All right. So if you go towards positive x, you see that as you move along the x direction, the potential energy is increasing. Okay. As you move along the x-axis from 0, the potential energy is increasing. This means that by this equation, the momentum will decrease. So if you start here and go towards the positive x direction, the potential energy, the momentum has to decrease because the potential energy is increasing. Okay, and at the point where E equal to U, that's at the point of intersection, at the point in x where E intersects U, the momentum is 0. All right. Okay. Now what happens? Now you just have to continue. If you go back in this direction, right? If you go back in this direction, you see that if you go from positive x towards 0, you see that the potential energy is decreasing. So the momentum will start increasing in the opposite direction. Okay, and then it will encounter this point where again the potential starts increasing from here. right? Again, the potential starts increasing and the momentum starts decreasing, and at this point the momentum becomes 0. All right, then the direction is reversed and again it goes like that. All right, because now the potential is decreasing. When you go from here to here, the potential is decreasing and the momentum increases and it reaches here. Okay, this is supposed to be an ellipse. All right. Now thus indicate the direction of motion of the representative point by marking tiny arrows. So this is how we drew it. We started from here, so this is the direction. All right, so it goes like this. So there's a trick too. There's a rule of thumb to remember the direction of these arrows. We'll discuss this soon. Okay, so this is the phase portrait. No, this is the phase space trajectory corresponding to one particular energy. What if the energy is E2? Okay, this is the phase. Let's say that this is the trajectory. This is the trajectory for energy E1. Okay, what about E2? Okay, if the particle or if the harmonic oscillator has energy E2, then you will get a corresponding curve along this line. Okay, you can actually imagine this thing. You can actually, you can actually imagine this thing. All right. Okay, so you see that harmonic oscillator in the real space, all right, these are not closed curves. In the real space, these are just oscillating, it's not a closed curve, all right? But in the phase space, it's a closed curve. The phase space trajectory is the closed curve, all right? Because the system starts at one particular state and then it returns to that state. Okay, it returns to that state. We are assuming that there is no dissipation or there is no loss of energy. Okay, so the system or the representative point must trace paths corresponding to constant energies. All right, and we'll see that paths corresponding to constant energies are actually ellipses for a harmonic oscillator. I hope this is clear. All right, so this is the general idea. We'll continue. Okay, next we said we have to elaborate a little bit about sketching the potential U of x versus x. All right, so we'll have to write down a few steps. So in your examination you will be given a potential curve, potential as a function of x, okay, and you will have to plot it first, okay, just to see the qualitative behavior of it. And then the second thing is to just draw parallel lines, all right, energy lines corresponding to different energies, and then you follow this rule and you get the curves. Okay, so it's an important thing to plot the potential U of x as a function of x. Okay, now I hope so much is clear so far. Let's move on to sketching the potential. Right? Now you can follow this strategy to plot the potential energy. To plot the potential energy versus position curve, we can take the following steps. Okay, first step is to find the points where the potential energy is 0. Find the points where the potential energy is 0. Right? Find the points where the potential energy is 0. Right? So we are actually talking about potential energy. So sometimes I just say potential, but that's not entirely accurate. We have to say potential energy. All right. So I hope you'll correct it in your mind. So find the points where the potential energy is 0. Right. So you take U of x and say that it's 0 and solve this. U of x equal to 0. Which are the points along the line where the potential energy is 0, right? So you will have this curve, okay, and you will plot the points where the potential energy is actually 0. Okay, you'll plot the points. So you got 3 points now. That's not enough, obviously. Suppose there are 3 zeros or 2 zeros. Let's say there are 3 zeros. We plot all these 3 zeros on the line. We mark all these 3 zeros just qualitatively, okay. Now the next is to find the extremum points for the potential energy curve, right? You need to find the extremum points, okay, the maxima and minima of the potential energy curve. How do you do this? You know how to find the extremum. You just take du by dx equal to 0. Solve this and you will get the points where the potential energy is an extremum. Okay, so for example, let's say that for x equal to a and some value a and x equal to b and x equal to c, you have got an extremum. Alright, so by constructing this equation dou e by dou x equal to 0 and solving it, we'll get a number of points corresponding to the extrema of the potential. Alright, these are points where the potential energy is maximum or minimum. Okay, these are the points where potential energy is maximum or minimum. Alright, we don't know which. I hope this is clear. Alright, so we can just mark those points. For example, let's say okay, let's just leave it at that. Alright, now it's important for us to find whether these points are actually maxima or minima. all right, whether these points are actually maxima or minima, all right. So the first step is to find the zeros of the potential energy. The second step is to find the extremum points for the potential energy curve by equating the first derivative to 0. We have got the extremum points. The next step is to find whether these points, okay, these extremum points are whether these are maxima or minima. What do you do for that? Now you find d square u by dx square. Okay, you find the second derivative and put x equal to a. All right, and if it's positive, then it's a minima. If it's negative, then it's a maximum. All right, this is the rule. Okay, if the second derivative at a given point, okay, at the point of extremum, we already have these extremum points. Okay, you take each point and find the second derivative at that point. All right, you find the second derivative and put x equal to a. If it's positive, we know that it's a minimum. If the second derivative is positive at a given point, then it has to be a minimum, okay, at an extremum point. All right, if the second derivative is positive at an extremum point, then that extremum is a minimum. All right, now if the second derivative is negative at an extremum point, then that extremum is a maximum. All right, now this information will be sufficient usually to plot the potential energy curve, all right, in a qualitative manner. Now, once we get the shape of the potential energy, we draw the energy lines and then we'll draw the phase-space trajectories. Okay, all right. So, find out whether the extremum points obtained in the previous steps by finding second derivative of the potential energy at the extremum. Okay. Find out whether the extremum points are obtained in the previous steps are maxima or minima. Okay, I'll just correct that. Are maxima or minima. We need to find whether this extremum is a maximum or a minimum. Okay, by finding the second derivative of the potential energy at the extrema. So if d square e by dou x square at that point, okay, at these particular points is greater than 0, then the extremum is a minimum, and if it's less than 0, the extremum is a maximum. Okay, I hope this is clear. Okay, we'll look into some examples and you know what I mean by these things. Okay, now there are a few more points that I have collected. These are basically rules of thumbs. Okay, so it's rules of thumb. You can just remember these things and it will help you. If you see a picture, it will help you to do these things. All right. The first thing is that the trajectories of the phase space never intersect for autonomous systems. So for autonomous system means it's not driven from outside or something. The Hamiltonian is the same. All right. You have a Hamiltonian, it's fixed. All right. So provided you don't change the rules in between. Okay, provided you don't change the rules in between, the trajectories in phase space will never intersect. Why is that? Why is that the trajectories can never intersect? Right? We saw that we talked about this conservation of information, right? So for every point in phase space, there has to be exactly one incoming line and exactly one outgoing line. All right. Why is that? Because we know that given the state of the system at any time, this is also known as determinism. All right. The state at any other time is completely determined by the equations of motion. All right. Given the state at any time, this is very important. Okay, this is true generally for all physics. Given the state of the system at any time, the state of the system at a future or the past, the state of the system at any other time is completely determined by the equations of motion. All right. So so the Hamiltonian, generally you have the equations of motion if you have the Hamiltonian. This means that the future of this system or the trajectory or the state of the system doesn't depend on all the history, right? It depends only at the state at a given time. Okay, give me the state of the universe at any time. Give me the state of the entire universe at any particular time. The future is completely determined by the equations of motion. All right, or take the state of the system at any time, state of the physical system at any time, the future is completely determined, which means that once this is the phase space, all right, once you pinpoint the point, once you say that this is one possible state of the system, all right, then the equations of motion will tell us what's the next possible state, all right, and what's the previous state. Okay, this is completely determined. Am I right? Okay, now imagine two phase space trajectories are actually intersecting like this. Okay, suppose two phase space trajectories are intersecting like this. Now this point is a problematic point, all right, because if the state is given, if the state at this point is given, we don't know what its past is, we don't know what its future is, right? It could be this or it could be this. This means that the evolution in phase space is not unique. If there are intersecting curves, that means that if the phase space trajectories intersect, then that means that there are points in phase space corresponding to which the future of the past are not uniquely determined. If the system is at this point, we don't know whether it will go along this trajectory or this trajectory. Okay, and there cannot be two futures corresponding to a given particular state. Okay, that's not allowed. That's known as conservation of information. That's also known as determinism, etc. This is a very fundamental rule in physics. All right, if you have a state, if the state is given, then its future and past are uniquely determined. All right, these are uniquely determined. There are no two futures. There are no two possible futures. All right, it is uniquely determined by the laws of physics. All right, this is the reason why the trajectories in phase space never intersect. All right, this is only true for autonomous system, because if you change the Hamiltonian in between, all right, then of course the evolution also will change. All right, but that's not the case we are talking about. We are talking only about autonomous systems. Means the Hamiltonian is fixed. The functional dependence of the Hamiltonian is fixed. Okay, all right. Every point in phase space will have just one incoming arrow and one outgoing arrow. All right, you take a point in phase space, whatever dimensional it is, you take a point in phase space, there will be exactly one incoming line and one outgoing line. Okay, because the laws of motion, it's also known as reversibility. All right, so suppose they intersect, and at this point, right, at this point we don't know what the past of the system is. It could be this or this. Right, imagining that arrows are like this, right, it could be this or this, but this means that it's not reversible. Okay, so but for physical systems, the equations of motion, the laws of motion are completely reversible. All right, so if you know the state, now you know what the state was in the past. All right, provided you know the conditions and the equations of motion, etc. Right. Now, if at any point the number of incoming arrows exceeds the number of outgoing arrows, then the law is irreversible, and we say that information is not conserved. All right, but information is actually conserved in physics. So we won't have some. So the point here is that the takeaway point here is that the trajectories in phase space never intersect. Okay. Now let's talk about marking arrows. We said that we need to mark arrows on the phase space trajectory. So a rule of thumb is that if the momentum is positive, at a point in the phase curve, then the arrow at that point is towards the increasing x direction, towards the right, right? So if the momentum is negative, then the arrow is towards the negative x direction. How do you see this? So suppose you have got this px thing, all right? In which cases are momentum p positive? All right, p is positive here and p is positive here. P is negative here and p is negative here. So if you have a curve like this, right? If you have a curve like this, you see that the momentum is positive. Okay, in this quadrant, the arrow has to be there towards the positive x direction. All right, also in this quadrant. Right. Similarly, if you have some curve like this here, right? It's in the quadrant where p is negative. This means that the arrow is towards the negative x direction. Okay, that's a simple rule to remember. This is true. Okay? So, for example, once you look at the simple harmonic oscillator, if you look at the simple harmonic oscillator, you see that the momentum is positive here, so the arrow is towards the positive x direction. The momentum is negative here, right? This is the 0 point. Momentum is negative in this quadrant, so it's towards this direction, left. And here again it's negative, so it's towards the negative x direction, like that. Okay, so that's how it is. All right. Okay, the regions where E is less than V. All right, so in the graph you will see that when the potential energy is negative, the energy also, total energy can be negative, but the kinetic energy cannot be negative. All right, so there are regions where E, the total energy, is less than the potential energy. In these regions, these are classically forbidden. All right, because in these regions you will see that the kinetic energy can become negative, which means that the velocity is imaginary, and such a thing does not exist in classical mechanics. Okay, so the region where E is less than V are classically forbidden, and it's very easy to see which are the region where E is less than V. We will see in some of the plots. All right, So the regions where E is less than V are classically forbidden, because in these regions momentum becomes imaginary, alright, or velocity becomes imaginary. Now phase curves for periodic motion are simple closed curve, because just half mv square, right, half mv square, right. If this is negative, that means velocity is imaginary, that's what we mean. Phase curves for periodic motion are simple closed curves, okay. So periodic motion in real space corresponds to open curves, it's not closed curves, but in phase space periodic motion corresponds to closed curves, okay. So periodic motion corresponds to closed curves in phase space, okay. Now there is a term called separatrix. Separatrices differentiate between different types of trajectories, alright. For example, for the same system, there can be trajectories which are periodic, which are closed, and there can be trajectories which are open, depending on the potential energy at a given point, okay. So for example, if you have a curve like this, if you have a potential curve like this, okay, if you have a potential energy curve like this, you will see that this, within this region, it's closed, all right, it just keeps going like that, right. But outside this region, you will see that it's free, it is free, the momentum, this is an open curve, it's not what you say periodic motion, okay. So it will be an open curve, okay. But in between these two possibilities, for a potential like this, for example, okay, in between these two possibilities, there will be curves which separate between these two possibilities, and these are known as separatrices, okay, all right. Now it's also one thing to remember this thing, it's a good thing to remember this thing, sometimes it will help you to eliminate some of the options. So if the Hamiltonian does not change under the transformation p going to minus p, okay, suppose the p appears as p square in the Hamiltonian, then even if you put p is equal to minus p, the Hamiltonian does not change, okay. Then the plot will be symmetric about the x-axis, because we are talking about px curve, right. This is where p is positive, this is where p is negative, alright. So this means that if the Hamiltonian does not change when you go from p to minus p, the shape of the curve will be symmetric, right. For example, this thing, it's entirely symmetric about this x-axis, it's entirely symmetric about this x-axis. It's also the same for x. If the Hamiltonian is invariant under the transformation minus x going to minus x, this means that this is x, this is positive x, and this is minus x. The curve will have exactly the same shape about the p-axis. It will have the same shape about the p-axis, or rather it will be symmetric about the p-axis. Alright. Now let's look at a general example. Right, some of the points are illustrated here, okay. So this is the potential energy curve, that we have. These are the energy lines, E1, E2, E3, etc. Alright, so this is x, u versus x, and this is v versus s. It also could be p versus x, okay, it doesn't matter. You see that this is E1, E2, E3. Now you look at this E1 line, alright, you continue this E1 line, you see that here this height is the energy, alright, this height is the energy. This height is less than this height, right. So in this region, the potential energy is less than the total energy is less than the potential energy, okay. It's clear that if you extend this line for E1, right, if a particle is with energy E1, then this region is forbidden, this region, okay, this region along the x-axis is completely forbidden, because inside this E is less than V, alright. So this region is forbidden, this is a forbidden region, okay. That's one point, alright. This line corresponds to E2, some other energy E2, and you see that at one point E2 is equal to U, right. At some point E2 is equal to U, right. So that will correspond to separatrix, because this is for E3, you see that it's completely unbound, right. It's completely unbound, it can go anywhere except beyond this point, it cannot go beyond this point, alright. Now suppose a particle is with energy E1, right. Suppose a particle is with energy E1, suppose it's coming from infinity, right. When it comes from infinity, it sees an increasing potential energy, right. We said that P is equal to square root of plus or minus square root of 2m E minus U, right. This is just to get the qualitative behavior. When U increases, P decreases. So suppose a particle is coming from plus infinity with energy E1, right, with energy E1, it will come here, it sees more and more of the potential energy, because the potential energy is increasing when you come from the positive, let's say plus infinity. The particle is coming from plus infinity with energy E1. Okay, so it sees an increasing potential energy, correspondingly the momentum decreases, and at this point the momentum becomes 0. At this point the momentum becomes 0. Right? It cannot cross this point. Because this region is classically forbidden. So for a particle for energy E1, right, the left side of this part is completely forbidden. It cannot enter this part. Okay, so it sees this potential, it comes to a rest and then turns back and goes back to infinity. Right? Now suppose for particle E2, particle of energy E2, it will come here, all right, it will approach this point like this, all right, it will approach this point, and depending, all right, so it will just approach this point, all right, this is coming from plus infinity. All right, so a particle with starting with a positive momentum, all right, it will go along this line. All right, so this is an example for a separatrix. Okay, for this point. Right, if it's more than this, all right, you see that the particle coming from plus infinity will come here. Its momentum will slow down. Its momentum will decrease up to this point. All right, its momentum will actually decrease, but it never comes to 0, right? It decreases and then again increases, like that it goes, right? Similarly, let's look at some other region, right? This is a general curve, right, just to illustrate the idea. Now let's look at this part. Let's look at this part, right? This part. So this corresponds to some other energy, E2, and it's already within this region, all right? It's already between, let's say, this x1 and x2. Okay, so what happens corresponding to that? You see that you have a closed curve, all right, because you could start the particle with any momentum, but as it goes towards the plus x direction, the momentum will decrease. It will come to a halt at this point, right, because at this point E is equal to U, right, it will come to a rest. So momentum goes to 0, and then it's this thing, all right, so momentum will go to 0 and it then just goes like that. But now corresponding to this line, you see that we have got a different kind of curve. That's known as a separatrix. Right? We have got a separatrix. Right? Now, if it's like this, if the energy is like this, then the particle is confined between, let's say, this x1 and this x2, and we have some sort of a periodic motion, because at this point the momentum will 0. These are turning points. All right, these are turning points. Okay, so you can look at the qualitative behavior like this. Right. So if given a potential, if we have a potential energy curve, we can simply, just by looking at it, we can draw the phase space diagram. Okay. All right. So for higher energies, you see that for higher energy, a particle coming from plus infinity, yes, its momentum will decrease, but it never goes to 0. It just keeps increasing and decreasing, and at this point it comes to rest. The momentum becomes 0 at this point. All right, because at this point E is equal to U or P equal to 0, and then momentum increases in the opposite direction, and then it goes back to infinity. All right, this is the general description of it. Let's do just one example before winding up this session, and we'll do more problems in the next class. Okay, in the next session we'll just do the phase portrait for a simple harmonic motion. We already discussed this, but we'll go through it in some more detail. The phase space portrait for a simple harmonic potential V of x equal to half kx square is equal to half omega square x square is sketched. All right, how do we sketch? So it's easy to see that this is an ellipse. All right, because what's the conservation of energy condition? We say that half, we can say that p square by 2m plus, this is the kinetic energy. What's the potential energy? It's let's write it as half k x square is equal to some energy E. Okay, this means that p square divided by 2me plus a half kx square is equal to 1. We just divide throughout by e. Okay, now we can write this as p square divided by 2me plus x square divided by 2e by k is equal to 1. Right? What is this equation? This is of the form x square by a square plus y square by b square is equal to 1, and this has to be an ellipse. This is an ellipse. Okay, so we immediately see that these are ellipses. right? Depending on the energy, these are ellipses with different what is the major and minor axis, right? The energy determines the major and minor axis, all right? So it's clear that this is an ellipse. Okay. And there is an interesting point called the equilibrium point, all right? At x equal to 0, there is a point at x equal to 0. The one trajectory I missed out earlier, okay? This is the potential energy, and we draw the curves like this. We said that if the momentum starts at some positive value, it just makes a closed curve like this, all right? What if the momentum starts at 0? What if p is equal to 0? Okay, then it will remain at x equal to 0, and this point is in itself a trajectory. Okay, this point is in itself is a trajectory. Okay, because if p equal to 0 initially, x is equal to 0, and it will remain there all the time. All right, it will remain there all the time. P equal to 0 and x equal to 0. I'm sorry, p equal to 0 and x equal to 0. That corresponds to a particular energy, and it will remain there forever. That's the possible trajectory of the system. Okay, all right. That's what the system at x equal to 0, v equal to 0, or p equal to 0 remains at the same point forever. The trajectories are ellipses. Right? I've plotted it here. So the first thing is that this plot is the plot of the potential energy curve. This is the plot for the potential energy curve, and we see that this is corresponding to different energies. We have got ellipses. Just as I said, when E at the points where E intersects the potential energy curve, the momentum becomes 0. Right? So these are what is a ellipses corresponding to turning points. Right? The energy determines the turning points. So, right? These are ellipses with turning points. Let's say x1 and x2 and x3, x1, x2, x3, x4, etc. And we have got ellipses here. Right? So this is not very difficult. And other regions are classically forbidden. Other regions are classically forbidden. All right? For example, if you just extend this energy line here. Okay, at this point we see that this height is the energy, all right, but the height of the potential energy is this, right? So we see that this is a region where V is greater than E, or E is less than V, and it is a classically forbidden region, right? Likewise outside here, all right? So the system cannot access the entire x-axis from minus infinity to infinity because there are regions which are classically forbidden. Okay, all right. Yeah, I think we'll wind up for today, and we'll discuss the rest in the next session. All right, maybe you can try obtaining as an exercise. Okay, before the next session, you can actually try to obtain the phase portrait for the potential V of x equal to minus half kx square. All right. So phase portrait means that we are drawing all sorts of curves for different energies. All right. We are not drawing just one diagram corresponding to one energy. We are plotting all sorts of possible phase space trajectories. That's when we call it as a phase portrait. Okay. Now we can try this at home. First you plot this and see how the trajectories behave, or how we can plot the phase space portrait. All right. We'll discuss this in more detail in the next session. All right. So for now we'll stop. Thank you.